Hello, everyone. This is lecture 18 of PTRE 465531, Petroleum Reservoir Geomechanics. Today we will do the second part of our review ahead of the first exam, which is going to be on Friday. Starting this time on Friday, so in 48 hours, you are able to start the exam, and you have, I guess, until 2:30 on Saturday or 2:29 on Saturday to start the exam. And once you start the exam, you have 50 minutes to complete it. I did the exams, which is why I slept at 5+ last in the morning. But there are two different exams, and there are two files uploaded. Make sure you do the corresponding file. Don't open the, it's called something like PTRE 465 underscore midterm exam 1 underscore SP 24. And the other one is PTRE 531 underscore midterm exam 1 underscore SP 24. Make sure you open the right file. Don't do the 465 if you are a 531. And please be very careful with the PTRE people. They are doing their jobs. I know it's an intimidating job. I already had reports, incident reports from the other class that how did they call that? Not involuntary disconnection, intentional disconnection or something. And these people are basically like, I have no option than to basically give them 0 because they end up leaving with the exam. What did it say? High priority. An incident report what has been processed. Did not erase whiteboard. Okay, that's easy to deal with. But the other one was an incident report failed to follow instructions, deliberate disconnection. This is more serious. Make sure you follow all the rules, and I don't know the rules off the top of my head. They are not written down by me. And yeah, I mean, getting in trouble makes it hard for everyone, even myself. So please avoid doing that. Anyway, so be okay with them, be professional with them, go in, take the exam, leave, bye-bye. And don't worry about the exam until you see the grade. Okay, we went over module 1 fastly last lecture, and today we'll go over the 40 slides of the module 2 that will be in the exam, that will be covered in the exam. We said for module 1, the most important thing was basically how do the fractures, mode 1 fractures open, and how do they propagate, and some other stuff that I said they are important, like the overburden stuff, how, hey, we have a new student. We have overburden estimations and stuff like that. We said that they are important. I tried to emphasize it as I go along. And the same thing I will do here. And I said, don't worry about matrix rotations. So don't worry about that RPG matrices. You are not going to see those in a 50-minute exam. You are not going to see those in that exam. Probably you are not going to see those in the entire semester, to be honest. Anyway, module 2 started with a brief introduction to solid continuum mechanics, which is the branch of solid mechanics dealing with transmission of forces, deformations of solid materials, blah, blah, blah. You basically model something as a continuous mass rather than discrete particles. And you want to know how stress relates to strain. Together, they make this relationship, stress to strain, is what we call constitutive relationships. It tells us how does the model behave, stress versus strain. Boundary conditions, you will need that in your code, let's say. It's stuff that we learned in the first module, like Andersonian stresses, in situ stresses, basically externally applied stresses, like things you externally apply on the REV. But the way the REV behaves, like in terms of stress and deformation as REV, that's the constitutive relationship. Then we went to Mr. Cauchy, who was a civil engineer from France, who was very smart. He took the force balance and arranged it a certain way, basically second law of Newton added up. And he came up with a summation in each direction to see how would a linearly elastic material behave. Basically, he did Hooke's law in 3 dimensions. He was the first one who had that concept. And we have this, there was a little bit of a confusion when I did that in class. I remember that this is compression positive. So you may have seen it in solid mechanics as tension positive. And then every arrow will look differently. It will look the opposite way. And we have the summation of the forces in each direction, X, Y, and Z. They should be plus the acceleration term is equal to the accumulation. And if I remember well, I did a mistake in the class when I was, I called accumulation the acceleration term, and the 0, I called it something else. But I think I fixed it after. We divide by the elemental volume, dx, dy, dz, and we end up with this set of equations that makes it easier. And we have basically the change of the stress in each direction, the change of the normal stress, the change in the shear stresses, acceleration. It's important if you have gravity, equals the accumulation in every direction. And remember, if you are steady state, automatically all the t's should go to 0. All the derivative by t, nothing changes with time. Okay, and then we did an example to apply it to the vertical stress. Basically, because we have the gravity, that's the difference between X and Y. Z has the gravity. We rearrange it, and we sort of back calculated or back derived the equation that we use for overburden in the first module, which I basically, in the first module, I threw it at you. Now I'm telling you how it was derived. It's very easy to understand. Kinematic matters is basically displacement versus strain. How do we quantify displacement? Displacement is it's more quantitative than deformation, but is less quantitative than strain. We need something to measure to be able to quantify deformation. And for that, we use strain, which is dimensionless. It's a very, very sort of, how do we call it? Easy, practical parameter to deal with rather than deformation. It takes the units away. It quantifies not absolute displacement magnitude, doesn't give you how much you elongated or you shrink. It gives you displacement variations in space, normalized actually by the initial dimension length. And we showed here how it is measured in the x-axis when it's elongation by delta ux, and how it's measured in the y-axis when it's elongation by delta uy. And then you can have shear, which makes things a little bit more complicated. You have angles involved, etc., etc. And these are things that you learn in solid mechanics in more detail. And you can find the angles at which the rotation sort of happens, or the angular displacement takes place, as we call it, theta in terms of pi, and the delta ux and the delta uy. Now, how about we put everything together in tensor? Okay, we have a strain tensor, just like we have the stress tensor in module 1. And you have the strains in every direction. And these are the expanded equations for each. And yeah, for Cartesian coordinates. Then we have some, it's 3 by 3, 9, but some of them cancel out, like E epsilon yx is the same as epsilon xy, right? They are the same.
That's what isotropic, right?
No, that's for stability.
Yeah.
Epsilon zx is the same as epsilon xz. So I have how many terms that are independent? 1, 2, 3, 4, 5, 6. Yeah. Yeah, it should be 6.
Yes, 6.
Yeah. Let's just take these 3.
Yes.
And then
the other one. Yes.
yeah, all they are. So 6 unknowns. And combined together, we can make the volumetric strain. In Cartesian coordinates, it would be like this. In radial coordinates, it would be like you did, I believe, in the homework. Or was it the homework last year, I think, that we did. Was basically for radial coordinates, it's gonna be epsilon zz plus 2 epsilon rr in the radial direction. So yeah, that's how we do that in when we do core analysis. Actually, that's how we measure volumetric strain. And I showed you a definition of how this is derived. It involves some approximations. That's why I wanted you to see that. You multiply this, and then you erase all the double delta terms. Those that have 2 deltas, get them equal to 0, because they are very close to 0, and then you end up with, and you divide by the original volume, you end up with basically this, what we measured before. Delta ux divided by delta x, by ux, plus delta uy divided by uy, plus delta uz divided by uz. And that's approximately in the direction that we mentioned before. Sorry, the format that the equation format that we saw before. So we talk about 6 unknowns, and then we went even simpler. We started talking about linear elasticity, but this is not the first time that we saw linear elasticity in this class. It's like we have been looking even in module 2. The tensor of strain, okay, it can be quantified using linear elasticity, and we have seen the stress tensor in module 1, but how do we combine them together? That's where linear elasticity comes to place. It's basically what we said, Hooke's law in 3 dimensions. We consider a 1-dimension displacement first. I apply a force Z to a body, and I get elongation delta Z. So let's see. It doesn't do it. I think it's going to do it slowly. Let me see. No. Maybe I will do it as a. Yeah, I have error here. Okay. There you go. Ooh. So I apply a force Fz on a cross-sectional area A. So the stress is Fz over A. And then I get elongation delta Z. My original height was H. So my strain that I induced was delta Z over H. And I relate that to the Fz over A, which is the stress, with a proportionality constant. Now I don't call it K as we learn in statics and solids, I call it E. This is what is known as the Young's modulus or the elasticity modulus. And it represents, it's a measure of the stiffness of the material. If the material is stiff, I need to apply a lot of stress to get this much small strain, right? If the material is soft, I apply very little stress and I get this stiffness, right? So I expect metals to have a very high Young modulus. And I expect softer materials like this to have a very low Young modulus. It's a compliant material. That's what we say, don't get complacent during school. It means that get like soft and basically don't take things seriously. So Young modulus is a little bit of a simple to understand proportionality constant because it involves stress in one direction, displacement in the same direction. So it's sigma II strain epsilon II. Excellent. Very easy. I apply stress in X direction, I get elongation in the X direction. That's all I care about. But what will happen in the other direction? So yes, I get elongation. I get elongation down. I got this elongation like this. I didn't make it good. I apply the stress and I got this elongation. Okay. But what will happen in the perpendicular direction? I will get shrinkage. I will get shrinkage most likely as well. And I should make it a different color because it's going to be confusing. But basically, if I only look at the okay, this is the new sort of shape. It got longer, but it also got slimmer. It got longer in the Z direction. It got slimmer in the X direction. So I have a new term called Poisson's ratio, which relates strain in one direction versus strain induced in the perpendicular direction. So epsilon JJ, epsilon divided by epsilon II. And because if you make it taller, it becomes slimmer, and if you make it shorter, it becomes fatter. I have the negative sign to take care of the changes in the direction that take place, sort of. We talked about typical values for rocks, and we said that the rocks rarely behave like at a fixed value. Maybe Poisson's ratio in the X versus Z direction is one value, in the Y versus Z direction is another value. There is heterogeneity, there is anisotropy. Remember, anisotropy has to do with changes with respect to direction. Heterogeneity has to do with changes geographically. Here I have a different set of properties than here. This is heterogeneity. Now, if here I get a different value like this and a different value like this, it's anisotropy. We also gave another example that the rocks have microcracks, and when you start stressing them, the first thing that will happen when you apply stress is that these microcracks will close down. So you are going to be reading a high displacement value, but that's not really the rock shrinking. It's basically the microcracks closing down. There was a question in my geomechanics final and geomechanics exam 11 years ago, fall of 2013, and not many people got it. It was asking, why do you get in a triaxial test, you will get young modulus to be smaller at the beginning than what it really is, because microclouds are closing first. And yeah. So you get displacement that is not really has to do with the rock shrinking. And then we talked about Voigt, I forgot his first name, Wolterman Voigt, something like that. Yeah. And he took all those equations that we mentioned together of Cauchy, and he said, okay, let's assume isotropy. And then we put them into one matrix. Yeah. And we are gonna do the matrix notation. Actually, he was the one who defined tensor as we know it. So it's he had contribution in a lot of stuff. But basically, he took all the relationship between stress and strain from linear elasticity, not Cauchy. Cauchy was the stress balance guy. Yeah. There were some people between the two. He put them together into a nice, neat matrix. So we'll see it. Okay, those are the shear. Those are the normal. Those are the shear. And yeah, this is important to know how to operate with this relationship. And that is, I want you to be very, very comfortable in basically making derivations from this matrix equation. So, and I know that you should know about those from linear algebra, but basically, what we do, and I did it fast in class, but basically you take this and you set it equal to basically this times this. And you go like, you go this, oh, sorry, this, and then you go down like this. So this E, big thing, times 1 minus Ni times epsilon XX plus this thing times Ni times epsilon YY plus this thing times Ni times epsilon ZZ. And then you have zeros. So it doesn't matter. But I want you to be very, very familiar on how to do matrix multiplications, rows by columns, etc., etc. It's not crazy stuff, but don't see this equation and get confused. Or like, how do you call it? Like that guy, deer in the car light, in the headlights. Yeah. Like a deer stuck in the headlight.
Oh, yeah.
Yeah, and these are quick stuff, okay? You can do manipulations using this matrix very fast. And you can see something like that in a 50-minute exam. This is basically relating stress to strain via the stiffness matrix C. Tensor, stiffness tensor, also known as. Now you can also do it the other way with the compliance matrix. It's the same equation, just reverse. I will give you both of this equation. By the way, I made the decision because you only have 50 minutes for the exam. I did something that could be stupid, but I put all the equations. I don't have everything at the front of the exam because some of you are taking, all of you are going to be taking PTRE exam, or like online exam, most of you. So I have the equations that you need after every question. So it's easier. You don't have to go back to the first page, copy paste or something.
You know the question, each question and each question.
Yeah. You're going to take the exam too? Huh?
I'll take next.
Yeah.
Anyway, oh, by the way, we also introduced the shear matrix, shear modulus. So we know Young modulus, we know Poisson's ratio, we know the shear modulus. Now, and there is two more. So we have the Lambda and yeah. So those, and I did fix the slides too. I had a typo here. I had the Greek mu, the lowercase. Yeah.
Is it a French one?
Yeah, it's the first time.
Yes.
So those equations, normal, 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 shear, shear, shear. Those are basically what you get from the Voigt's equation, just with two different set of variables. So you can relate Lambda to Young modulus and the Poisson's ratio. You can relate Lambda to shear modulus and bulk modulus, etc., and so on and so forth. This is the version. It's unlikely that you will see Lambda stuff in the exam because it's very hard to explain what do they mean physically. It has to do with the speed of sound through the solid object, etc. It's not as easy to understand like what was it, the Young's modulus and the Poisson's ratio. Now, the last one is the bulk modulus, which is a more volumetric kind of modulus. Remember, 6 equations, 6 unknowns, right? 6 moduli. But you only need 2 to get the remainder 4 because they are all interconnected. Yeah. So the way I apply confinement to a material, volumetric confinement, that means in every direction, and I get certain volume change, then I can use it to calculate the bulk modulus K, which is the inverse of compressibility, and it's related to the porosity of the material. So the bulk modulus is in PSI, compressibility is in inverse of PSI. All the moduli except Poisson's, and I think one more, one of the Lambdas is dimensionless, if I'm not mistaken. It's not just Poisson's that is dimensionless. Everything else is in one of the two. We can see. Let me go back to see. Lambda parameters. Okay, the first one has units of pressure, looks like. Yeah, the other one has units of pressure. Yeah. Bulk modulus has units of pressure. Yeah. What else has? Poisson's ratio doesn't have. Young modulus has. Shear modulus. Shear modulus. It has E on the top. Yeah. That's the plain elasticity modulus, which is just made up modulus. So all of them except the Poisson's ratio sounds like. Well, that's why they call it the ratio, I guess. Anyway. Yeah, here is how they are all interrelated. You need 2 to get the other 4. Okay. You need 2 and you get the other 4. And you read that in your homework. By the way, the homework has been graded and the solution key has been uploaded. And Mr. Kalu said that the results were 90, 89, 95, 95, 91.5, 94, and 88. So the highest grade was 95, the lowest grade was 88. That means it was good.
Not bad.
So far.
For me, I took 102 and Hakim like 105.
Yeah. Roxo, what did you get?
Yeah, I can't get it. I can't be in the class and get you a man. No.
You got 69.
Hey, this guy is good.
I can't be in the class and get you a man.
Yeah, it was.
Yeah, ego,
That never happened to me.
strong boy. From, what's the university? Aberdeen University, yeah?
No, it was Robert Gorton.
Yeah.
No, this guy was
Yeah.
Aberdeen.
Robert Gorton
Yeah, but they didn't have any.
in Aberdeen.
Ah,
Yeah. So yeah, this is how obviously you don't need to memorize that for the exam. If I need you to use it, I will give it to you. I'm not gonna give it to you because you won't need to use it. But you need to know that you need 2 to get the remainder 4. And you need to know that in your whole life, not whole professional life, sort of. It's an important, regardless if you work with rocks or any kind of solid material. Yeah, you basically 2 and you get the remainder 4. 6 equations. 3 normal, 3 shear. Some example problems. And then we started saying, okay, what is different for rocks than the plain sort of a pure linearly elastic model? And we said that in the rocks, we have pore pressure, we have pores, the pores are filled with pressure, with fluid, the fluid has pressure.
Yeah.
Yeah,
And this pressure are only against the
Sorry.
normal stresses.
yeah. And we incorporated that into the matrix,
Yeah.
right?
For us, is minus IPP, the identity matrix.
Yeah.
and stuff, yeah.
And it doesn't matter if you put the PP before or after the I. The same thing. Where was I? This is the expanded version, sorry. Sorry, I was pressing the mouse very fast. You must have got the people online busy. But basically, you have the expanded version here. And that is with static pore pressure. But the pore pressure doesn't change, fixed value. And yeah, it's subtracted from the normal stresses, not from the shear stresses. Then we did a little bit of we started going into what we use in research. As I made you an example problem where we have a gigantic like semi-sphere and it's huge in the X and Y direction and finite in the Z direction. And basically we have epsilon ZZ, but epsilon XX and epsilon YY go to 0. And basically that's the plane strain hypothesis that many geomechanics simulator systems use.
That's
Right.
why X and Y, they are assumed as 0 because it's huge and we are not gonna see any difference.
Yeah, it's
Like
plane strain. You have only one strain direction, plane strain. You can also have plane stress assumption,
Yeah,
which is for different kind of problems.
but you cannot assume that the stress are 0 and
Yeah, then it would be, you're gonna be getting a trivial solution, 0 equals 0. Apply the assumption, and basically, when we apply that assumption, we went back, and I remember that wasn't a good lecture. I was like, when I left from here, I was like, that's a bad lecture. But basically, and I did it again the next time, hopefully the second time I got it better. But we take these equations or the original version, and we set, what did we do? We set this equal to 0, this equal to 0, this not equal to 0. And then we did basically the first 3 rows with the, I mean, you don't need to worry about the second 3 because they are 0 times 0. And we came up with two equations, one for sigma xx, which is equal to sigma yy, and the other one for sigma zz. And we combined those, and we came to some very familiar equation, which is something that we find in the advanced drilling, which is basically from fracture gradient correlations, equations that are used. This mean divided by 1 minus mean times sigma zz. The plane strain theory allows us to approximate a lower bound for the fracture gradient, meaning pressure at which the fracture initiates. And you know, when you go to research, there is like fracture initiation. There is so many fracture initiation types, and you need to find the smallest one to calculate the value from. There are several equations for that. And also it depends on what environment you are. Remember, leak of testing measures S3, not SH mean.
Yeah, that's pretty good.
What if you are in a reverse faulting stress state?
Yes, we.
And so the people who took advanced drilling with me have seen this equation in the past.
So do
Or
you mean
eventually.
like they don't need to use S3 in reverse faulting? They don't need to
No,
use
in reverse faulting, the difficulty is to get fractures that are transverse to your wellbore. You are going to be getting those pancakey fractures. That are,
in a
no,
horizontal
they are
way?
like this.
No, in the horizontal way.
In a horizontal
Oh,
way,
yeah.
yeah. Vertical well, you are going to be getting transverse fractures like this. Yeah, you are going to have the problem they had in California in the diatomite.
How they used to avoid that?
They used to make two transverse fractures and go in the middle and try to get a longitudinal one.
Because on the crash,
Yeah.
shadow.
Yeah,
Yeah, to cut it.
I met the guy, one of the guys who came up with this pattern when I was at LSU. He was an LSU alumni. Huh?
Button?
Yeah, there is a pattern for that from the 80s. And he told me the whole story. These people were hanging out with people working in the aerospace business, and somehow they got the idea from that.
Because of the hydrodynamic,
I don't know. They
Yeah.
basically came up with relaxation considerations of how they're like you need to make the two fractures, wait a certain time, and
Yes.
then go in the middle and
It's
get
about
the
the stage
longitudinal.
after fracturing the first.
Yeah. It was it was a family of patterns that they had to find.
They got it?
Yeah, from the 80s.
So when you have a pancake, if it's vertical, it's like that, right?
Yeah, it's gonna be
And
transverse.
it's horizontal, it's like that,
It's gonna be
or it's still
it's gonna be like that, yeah.
like that?
So remember the name longitudinal or transverse has to do with the orientation with respect to the well. So if the well is vertical, a transverse fracture is like that.
Okay.
But if the well is horizontal, the transverse fracture is like that.
How about pancake? Is it not transverse?
It would be longitudinal in the horizontal, but this is the longitudinal in the vertical well.
Yeah.
So from vertical wells, you want longitudinal fractures. That's how it used to be. But from horizontal wells, you want transverse. Transverse in general are more difficult to get in. Okay, let's see that then, since you are.
One time I saw one guy who was talking about the fracture geometry, like of a vertical.
Uh-huh.
Sometimes it turns with distance. Is that true? Or
Yeah, because
like it goes like longitudinal and it goes like reorient the direction.
that's true because when you move away from the well, the impact from the well stresses go away. One second, let me find a quick video from somebody who did well. Where are we gonna see it now? I don't have it in my slides of this class, it's in the other class. There is somebody who goes into gelatin, he goes shallow, gets a transverse fracture, goes deeper, and then gets longitudinal fracture. This is what I wanted to show.
What regime would be that?
It would be reverse if you are shallow, and then it would be
But does it exist in real life that you have two regions at different levels?
yeah, of course. You can have it, maybe not too extreme. It depends on where you are. Okay, how do I don't want sound, but basically,
You mean that the map of the guy is not is at
there might be a transition somewhere.
He was talking like he has a vertical one and he has like fractures going like that longitudinal and then turning at some certain
Yeah. You can have them as you move away from the well. We're gonna learn about those in module 3. Yeah. So this guy, look at him. He has a jar of gelatin. It's pretty confined. It's allowed to displace only in the vertical direction. So it's pretty plane strain. He goes in, gets a fracture that is like this. Wait, let me draw it. Okay, this fracture is transverse because the well is vertical like this. And the fracture is like this. I always use blue for transverse from my PhD time. I'm probably gonna, yeah, I forced Nassim to do the same. Now, let's go deeper. Don't renew. Okay, now he's gonna go deeper. Say, drill deeper, basically. I don't know if he used the same hole, I don't think so.
It's new gelatin.
Way deeper. So more overburden above you. As V increases. And now look, longitudinal. Why longitudinal? Because, hold on, let me get this stupid pen. Where is Roxo? You see, we can't even keep a new student in the class. He left.
Yeah, but where they are like.
Okay, this is the well, but the fracture. Yeah, I will do it red to be consistent with myself. Is longitudinal. And now a good way to see it is that he's gonna rotate the jar and you're gonna see it from the side that it's very clearly a tensile fracture. He's gonna rotate. Look at that. People who say that gelatin doesn't do good reservoir analog. It's very much a tensile failure. Okay, the rest we don't care about for now. But what happens, and I think I wrote an explanation on the video. Where was it? Behind. I think there's an explanation on the video that is good, which I wrote. There you go. At low depth, the total weight of jello above the injection point overburden stress load is small, smaller than that of the stresses acting laterally. Therefore, the fracture at the first fracture initiates transversely. Fractures like this one, tensile open mode, yeah, I gave them a very good explanation. Even I talked to them about the diatomite. Yeah. Yeah. It was for grown-ups. It had math in it. Anyway, so we did the gradient. We talked about the gradient, the fracture gradient, and this is a simplistic approximation that if you are in a normal faulting or strike slip faulting, you are trying to open against SH mean, but it's not always it's not universally the case. So don't use this as SH mean universally, because you may be very shallow, you may be in a reverse faulting stress state, It's not always applicable. It's not universally applicable. That's what I was trying to say. And the typical value, definitely don't use that blindly. The 0.62.
So in reverse faulting, what will be the equation?
In reverse faulting,
Delta SV?
yeah, it's PSV,
And then
which you may know from the overburden. So you can use the overburden equation for that in a reverse faulting, right?
Or but if we go, let's say we go with this way of testing, we go delta SV and then delta SH mean?
No, it might be. It would be either, if that's the case, SH mean would be equal to SH max. Because remember, sigma XX is sigma YY, but then you are gonna have sigma YY and sigma ZZ. Sorry. No, sigma XX is equal to sigma YY, so SH max is equal to SH mean. And I think you may have one of those here. I think so. But bottom line is, if you do a leak of test on a reverse faulting, you get an overburden indication, right?
Which is
You're
S3.
opening a fracture, yeah, that's the S3, of course. Yeah. Unconfined versus confined uniaxial strain. I think here I made it clear that Roxo, was anybody waiting outside?
No,
A new class waiting to get in?
no.
Okay,
It's-
good.
nobody was out.
Good. Yeah. I want to stay a little bit longer if needed. So basically, confined versus unconfined is like, do you have confinement or do you don't have confinement? In the lab, most of the times, or the simplest laboratory measurements are in unconfinement. You find different values if it's unconfinement
Yeah.
versus if you have confinement. Nothing from here of essence. It's gonna come important. It's gonna become important next module when we do about UCS and this kind of testing. Plane strain plane strain modulus E prime is a more or less a made-up term, just to make our life easier. There is a term that basically appears many times. We group it together. I wrote recently a paper on that involved this kind of equations. It helped me a lot that I could define a plane strain modulus, but some people argue that it has some physical meaning, but it's not a fundamental physical meaning in the sense of it's a made-up term, you know? It's like it's not a primary. It's not a primary sort of independent variable, let's say. Okay. Yeah, you make some simplifications and you come up with a plane strain modulus, okay. Which came from the plane strain theory. That's why it's called like this. And then we talk about compressibility. Compressibility is important in a broad sense. I want you to know how you get compressibility if you have bulk modulus, for instance. And how do you get them? Because I have this equation. This is from reservoir engineering. This is what you use in a reservoir simulator. It's for fluid flow, but it has compressibility in it, total compressibility. Okay, this is a mixed term. It's an effective term. Because when you are modeling fluid flow, you are modeling fluid flow in a porous medium.
Yeah.
And you have compressibility of the rock. You also have compressibility of water in it, oil in it, gas in it, depending on what you have, and the rock in itself, of course. And we have this equation for it. And by the way, if I give you a bunch of equations, doesn't mean that you have to use all of them in the exam. There might be equations that are a little bit redundant. Or there might be equations that are two different equations for the same thing sometimes. You have to figure out, here is a correlation. It's good for a certain range, of C rock, the rock compressibility to the porosity. It's an experimentally derived correlation. It's not amazing for everything. But if we take that C rock and we convert it to pore volume divided by the original change of pore volume by pressure divided by the original pore volume, we get basically how does the SV stays constant, what we call uniaxial deformation, basically. It's like having imagine the bucket of where the jar where the jello was. Okay, the jello will stick on the surface, which makes it difficult to, but imagine I can compress the gelatin down because it's empty on the top, right? But in the X and Y direction, I cannot, because the walls are much stiffer than the air, I guess, or like so there is basically, that's uniaxial confinement. It's like,
So you are compressing only the pores, not the solids.
yeah, how do you call that? It's uniaxial deformation. You can only get epsilon ZZ, epsilon XX, and YY are zero, right? So it's just a plane strain, I guess. I'm forcing it to act like a plane strain. Yeah. And yeah, it changes. I divide everything by the I assume that is equal to the change in the pore volume. And then basically I have to, I convert that to basically an expression for the rock compressibility divided by, is given by the bulk, how do you call that, CBP? I forgot the name, bulk compressibility. Yeah. Yeah, well, leaving. Okay, so this is an important one. Yeah, and that is the last slide that you need to know. Make sure you guys know this equation will be important. Where was it? This one here, the green one. Sorry. C rock equals CBP divided by phi. I'm gonna give it to you, but yeah, you might see it again. Okay, and this one for porosity is important. And with that, thank you very much. Good luck in the exam. And I'm available if you need if you have any questions, etc., etc. Thank you.